Welcome back to Wheeled Mobile Robot course. So this is a lecture 9. You know, like lecture 8 we were talking about generalized wheel model along with the example. So and I gave a brief introduction there itself. We would be classifying the mobile robot, that too like wheeled mobile robot, into different category. So that is what we are trying to cover in this lecture 9, where we would be talking about, you can say, wheel configuration. Based on the wheel configuration, what would be the nature of the total mobile base. Based on that, we would be classifying and we would be seeing little further how this classification can happen and what would be the, you can say, seriousness on this. So if that is the case, what we will actually like see here. So in this particular lecture, we would be seeing about types of mobile robot based on the wheel configuration, and we would see the kinematic model, and in that one particular aspect what we have seen, that the W, which is nothing but the wheel you can say configuration matrix or input configuration matrix. That matrix, how it would actually like play for this particular what you call holonomic or non-holonomic. So now I already talk about holonomic. So we will just talk about how we can classify the mobile robot, that too like wheeled mobile robot, based on the kinematic or wheel configuration. If that is the case, I mentioned that it can be classified two broad way. So one is holonomic, the other one is non-holonomic. The name itself says that holonomic. Holonomic means it is having all the features, right? That is what we are trying to see in a synonym as such. So in that sense, what we are trying to see, a robot is holonomic if all the constraints that it is subjected to are integrable into a positional constraint of the form. For example, if I say that it is in a planar, so I can write a 3 constraint equation. All 3 constraint equations should be integrable form. So that is what we call holonomic. It is actually like quite tricky, right, to understand. So that's why we are actually like going to define this holonomic and non-holonomic based on the wheel configuration matrix. But before going to see that, then what is non-holonomic? So if anything, any constraint which cannot be written in this you call integrable form, then what you call that is non-holonomic. One simple example, you see the last class what we have seen as a differential wheel drive, where U and R only would be the component when you write it. So the V component was not coming. In the sense, the V equation if I write, that would be 0. So then somebody can say that it is integrable form because V is 0. If I integrate, that would be giving as a constant. Yes, I do agree, but that is not the real integrable form, right? Because V equal to 0, the constant can come anything when I integrate. But I need proper you call integrable form, that if I able to write all the constraint equation, then I call that is holonomic. So if that is the case, what one can easily feel it, okay, if the number of you can say controllable inputs is equal to number of degrees of freedom, then you can say holonomic. Yes, certain extent it is right, but not for all the time. For example, you would have seen the skid steering, right? Why it is called skid steering, I did not told there. So you can see that this robot, if you have actually like simple differential wheel only 2, that actually like give what you can feel it, it is just it would rotate and as well as it is actually like maneuver. But now you have 4 wheel and 4 wheel independently you control, what happened, you can see that it would be going very fast and as well as it is actually like sliding in the way in the real time. That is why it is actually like called skid steering. It is not a steering system, but you can actually like apply based on that the rotational can happen by skidding. So that is what the idea. So in that sense, what the number of controllable inputs for that skid steering robot, there are 4, right? But that is not holonomic system. Why? The V is still in non-integrable form. So that is why I said certain extent you can say that that number of controllable degree of freedom is equal to the total degrees of freedom, in the sense the number of input is equal to the total degrees of freedom, then you can actually like say it is holonomic system. So it is actually like you can see the overall picture, right? So now I am just giving a small you can say pictorial view. You can see this is a non-holonomic, it is a differential wheel, there are 2 power wheel and 2 casters are there. But you can see that based on the configuration it is a fixed wheel, the lateral direction is going to in a non-integrable form. So that is what we are actually saying, this is non-holonomic. Whereas you take here, because of the passive roller which is attached in this magnum wheel, so what it is giving, it is actually like giving all 3 constraints can be written in a integrable form. So that is what we call holonomic, and most of our robotic community people call it is omnidirectional or omnidirectional. What that mean? So it can actually like maneuver longitudinal, lateral and as well as rotate freely. That is what you call omnidirectional. So you can actually like resemble what is omnidirectional wheel. The wheel can actually like go in longitudinal and as well as it can slide in lateral. The same way this particular robot which is having all three, you can say, motion possible, that we call omnidirectional robot. So now you got a clarity, right? What is non-holonomic, what is holonomic, right? So now we will move forward why the wheel generalized model is required and why the W matrix is coming into a picture. So now we will recall. So the known mobile robot kinematic model is nothing but eta dot, you can write as J psi into zeta. But what we have written based on the generalized, you can say, kinematic model of the wheel. So what we brought, the zeta you can write in the form of W into omega, where W what we call wheel input or configuration matrix, right. So now can I actually like bring this non-integrable instead of writing non-integrable, you can say, a constraint equation, can I take this W as the nature of W, can I classify non-holonomic or holonomic? Yes, you can do. So for example, if you take a land based system, so what would be the W rank? So it would be actually like the left hand side, which is zeta. So this zeta is actually like would be having 3 cross 1, whereas the W can have maximum 3 cross n. The n can be less than 3 or more than 3, but what one can see, the maximum possible rank for the W is 3, and how many motions are required? 3. So if you have actually like a rank of 3 of W, then you can call that is a holonomic robot. If the rank is actually less than 3, what one can see, at least 1 or more motions are not possible. So that is what we are actually trying to say. So the omnidirectional and non-holonomic I am classifying based on the nature of the W. What I said, that omnidirectional robot is if the rank of W is 3, if the rank is less than 3, then I call non-holonomic. So now you got a very clarity picture, right. But a further end is actually like coming into a picture. What the further end? If you are going further, inverse differential kinematics. What inverse differential kinematic? The zeta you can write in the form of eta dot. So what you do, J inverse into eta dot. But now you assume that I can obtain, because the J inverse always exists, because the J inverse is actually like possible because the J is a simple orthogonal matrix and the psi is actually like, even if you put 0 or 90, that would be no longer singular. So in the sense you can see like you can always get zeta based on the eta dot desired. But what we are actually looking at, we are looking at the point of wheel configuration where the omega can I obtain. So for that what we will take, the W inverse into zeta would be giving as a omega. So now the W inverse is exists or not, your big question, right. Why? The W can be a rectangular. So if it is a rectangular, so what one can see, so the inverse is exist or not. So if it is actually like W, I write in a, you can say, real form, where it is actually like a real of m cross n, in the sense m cross n as a matrix. So what one can see, if this m equal to n, we are easily find it, right, because we assume that m equal to n, in the sense it is a square matrix. In addition to that, so this is having independent columns or rows. So what one can see, the singularity is no longer exists, in the sense W inverse is exist. Why it is so? The determinant of W is non-zero. So in that sense what you can find, the W inverse you can find it with the help of adjoint W divided by mod of W, which is nothing but a determinant. So now the determinant of W is exists, then you can do it, right. So now this is actually like one case, but now imagine this is a rectangular, okay, where m is actually like greater than n. So what that mean? So your number of, you call angular velocity, in the sense number of powered wheel or number of controllable inputs are less than the total number of system states. What that mean? So you have 3 are the states, but your number of wheels, powered wheels, are actually less than that. You take a differential wheel, so where that is having 2. So in the sense 3 less than 2, right, or you can say 3 is greater than 2. So in the sense what one can see, if it is a non-square matrix, so if you have actually like independent columns, in the sense here what would be the independent columns? So it would be 3 cross 2, right. So in the sense if you have independent column of 2, then what would be the maximum rank? So n. So in that sense what one can see, can I actually like find the inverse? That is what whole idea, right. Whole idea is actually like the zeta is given, can I find the omega, which is what you call angular velocity vector of the wheels. So can I find it? So for that we are trying to use a pseudo inverse, which is nothing but Moore, Penrose, we are actually like using it. So what we can call a lift inverse can be applied in this case. So we will see detail about the pseudo inverse in the further slide, but now you are calling lift inverse. Why it is called lift inverse? So this W plus you multiply with W in a pre-multiplication, then only you would get identity. But if you are putting W into W plus, that won't give identity matrix. So that is what you call lift inverse. So that is what we are actually like taking it. So now you can see that the pseudo inverse using, you can say transpose. So in the sense W transpose into W will give a square matrix, I can invert it. So that is what we are doing it here. We will see in detail how this W transpose W has come. Okay. So similarly, if it is actually like the other way around, non-square, but it is actually like where M is actually like less than N. For example, you take a magnum wheel, 4 magnum wheel drive. So where N would be, you can say omega 1 to omega 4, where N is 4, but you have UVR in the sense 3. So 3 is actually less than 4, in the sense what you can see the non-square is exists. Here what would be the maximum rank you can expect? So 3 in the sense, so M. What you can actually like call it, if it is having a linear independent rows, so what would be the pseudo inverse possible? That is what we are trying to use it. So earlier we have taken left inverse, so obviously what we call here is right inverse. So that is what we are applying it. So here W plus what you call, that would be coming with, you call right inverse. So now W plus can be actually like post multiply with W, then only you would get identity matrix. So this is what we call right inverse. Now there would be one question will come in your mind. So how you are saying that this W transpose whole inverse, earlier case W transpose and W whole inverse, what is the logic? So obviously I am trying to address, although it is not exact part of this course, but I thought I can address little bit on this. In the same the case 1, so you know like a simultaneous equations, right? So now you bring in that way as a mathematician, you can bring it. So there are actually like more equation than unknowns. What that mean? If you have actually like M is 3 and N is 2. So what you will get, the N is unknown, which are actually 2, but you have actually 3 equation to be written. So what that mean? So your equation is actually like over specified, because you have only 2 unknown. These 2 unknown you have to put, you can say put it in the 3 equation in such a way that this would be qualified. In mathematics this is no solution exists, but here what we are trying to find out, since no solution exists, if you leave it then the differential wheel drive or you call tricycle and all won't work, right? Then we have to see what we can do it. So this particular situation what we call over specified. So in the mathematics we will take one of the tool what we call least square method. So what we are trying to take, I am taking one of the parameter what I call L. So L is actually like length of the vector. What that vector here? So zeta is equal to W into omega. So now I am bringing it that as zeta minus W omega should be 0, but that is not possible in this case. Why? Because there are only 2 unknowns. So then what I can do, this length can I reduce to 0 or minimum. So in that sense what I can bring as a, you call objective function L as the length of the vector, I am taking as, you can say 2 norm of this zeta minus W into omega. So this I can write in a inner product style, in the sense zeta minus omega, sorry, W omega whole transpose into zeta minus W omega. So this is what you can write in a inner product form. So now what I can do it, so this L, if I actually like take differentiation with respect to what we wanted in a omega form, right? If I actually take dou L by dou omega, what I will get? So I will actually like get something useful, right? So what that can be either minimum or maximum. If I take dou squared L by dou omega squared, if that is actually like, you can say positive sign, then you can call as a minima, right? So now bringing that into a case, I am trying to bring actually like dou L by dou omega equal to 0. So now I am actually like differentiating this equation, partially differentiating with respect to omega. So then what I will get? So the equation would be giving, because this is actually like as similar. So I am keeping this as a transpose whole term as single, and this I am actually like differentiating. So in the sense it would be minus W, right? So in the sense I can rewrite this in this form. So now I am not done. So what I am not done? So I did not get it still the equation, right? So what I can do it, I am taking this equation further. I am actually like taking the transpose throughout, in the sense zeta transpose minus W into omega transpose, where the minus sign also I am taking into account and I am multiplying with the W. So, what I will get, minus zeta transpose into W plus W into omega whole transpose into W equal to 0. So, now you can see that something we have got it, right. What we got it? So, I can rewrite this equation in this form. So, now you can easily see, right. So, what you can see? So, if I take the transpose both side. So, what I will get? So, I will get W transpose into zeta, the other side it would be in the form of omega, where W transpose into W. What you do not know? Omega. You assume that zeta is known. So, then what you can see? You take the W transpose W, which is nothing but a square matrix. We assume that the determinant of this W transpose W is not non-zero, then you can take inverse. So, that is what we have taken. Now, you can see that what happened, the left inverse, right. So, if it is actually like over specified, what you obtain? You obtain the left inverse. Now, W, if you have given as a rectangular where m is actually greater than n, you can apply this, right. So, this is what the Moore-Penrose have given, this is what we call Moore-Penrose pseudo inverse. So, this is what we have finally written in the normal form. So, now only one condition is W transpose W determinant supposed to be non-zero, right. This is the condition, where W plus I am writing as a left inverse. Now, we will come to the second case. What would be the second case? So, there would be less equation than unknowns, where m is actually like less than the n. So, you take the same case what we have discussed earlier, you take the magnum wheel, there are 4 and there are number of, you can say, states are 3. So, 3 is actually like less than 4. So, now what we are actually trying to see the situation, it is underspecified. Why it is underspecified? So, you have actually like more unknown and less equation. So, now the unknowns you can actually like manipulate in number of way. If you talk in a mathematics form, this would have multiple solution. Theoretically, it is having infinite number of solution. So, then you can see this is not at all specified, right. In fact, it is not at all specified. So, that is why we call the solution is underspecified. So, obviously, you can see there are several solutions which will give zeta minus W omega equal to 0. Then what we wanted? We wanted which solution will give minimum length. So, that is why we bring it as a minimum norm method. So, what then? So, you have to take the length, that length would be fulfilling one constraint. So, earlier what we did simple optimization, but here we are doing a constraint optimization. What that means? So, minimum is what we are interested, minimum omega, in the sense length of the omega should be smaller. So, for that the length we are trying as a norm. So, here 2 norm. So, minimum of, you can say, 2 norm of omega subject to what? So, the zeta minus omega, like W omega supposed to be 0, that is what whole idea, right. So, if that is the case, what we can bring it? We can bring it these two in a single optimization equation, where Lagrangian multiplier will come, because there is a constraint equation, right. So, I can write the earlier equation in a different form. Earlier equation is straightforward, but now it is having a constraint. So, in the sense L I can write as omega transpose into omega plus I am bringing the Lagrangian multiplier, which is you can say lambda transpose into the constraint equation. So, now what you can see, this can be minimum in 2 instant, where actually like it can be minimum based on lambda, based on omega. So, in the sense what we can see, we can actually differentiate, partially differentiate this L with lambda and as well as omega. So, both supposed to be 0, in the sense 2 unknowns, 2 equation you will get, you can find it, right. So, I am taking dou L by dou omega. So, you know this is the equation, I am differentiating with respect to omega, I got this equation, right. Similarly, if I take a differentiation with respect to lambda, this is what the equation. Now, you have 2 equation, 2 unknowns. So, we will try to bring one first unknown with another unknown as a relation. So, the omega transpose I am writing into a lambda form. Since it is omega transpose, I am taking transpose throughout. What I will get? Omega in the form of half W transpose into lambda. When I see the second equation, okay. So, what I can actually like find it? So, zeta minus W omega equal to 0, this is not giving any usefulness, because this is what we started, right. But what usefulness is giving? This particular equation 23, you substitute into this equation. So, what you will get? So, you will get this, right. So, now you can see that this particular equation is having only one unknown, which is nothing but lambda. So, I am rewriting this equation in this, you can say, simplified form, where this half I am bringing it one side and you can see this is what the left hand side and right hand side. So now what is unknown to us? The zeta is known based on the inverse differential kinematics, the lambda is unknown. So you can actually take that what we have done, we take the W into W transpose inverse. So now this is what the idea. Now what is lambda? So lambda I can write in the form of what you call omega, and if you recall, the omega I have written as half into W transpose into lambda. So now I already found the lambda, right? I substitute that into this equation. So what I will get? Omega. So now you can see that the 2 and 2 goes out. So what you will get? So the right inverse, right, where W into W transpose inverse is multiplied with you can say post multiply in the case with the W transpose, that is what you call right inverse. So you got it, right. So what is the basis of this pseudo inverse have come, that you have clarified here. So now you can see that this W plus for both the cases we have calculated. Only one condition is the square matrix what you are obtaining, W into W transpose or W transpose into W, that determinant supposed to be non-zero. Okay. So this is the condition. So now you can see that we are almost ready to take off in a mobile robot more close to the real time. What more close to real time? So far what we have simulated is only a bare rectangular base as the vehicle, and we have tried to simulate. But now what we got it? We got the wheel configuration and we obtained the W matrix, and then we can actually like do the more, you can say, realistic simulation. So that is what we are going to cover in the next class. So where the next class would be focused on more about what we have derived in the lecture you call 8 and what we have derived now in the lecture 9, these fused, and we would be doing more realistic simulation which is more close to the what you call reality. So in that sense, lecture 9 what we have covered, so what is actually like the non-holonomic and holonomic, and now we know like what to be done in the further end. Okay. So now lecture 10 we would be seeing more on the kinematic simulation in the MATLAB base. With that I am actually like saying thank you and see you at lecture 10.